Look, the way I solve a problem, it's a slam dunk alley-oop. This is 1663 smallest string with a given numeric value. Boom, son. Let's go ahead and get right into this. You guys like my degrees? See that? See that? All that I learned. All of this. Nothing to do with anything I do on a daily basis in my job. Didn't make me more articulate. Didn't make me more intelligent. Didn't really contribute to my capacity to really do anything. Yet, I framed them and put them on the wall. Why are we talking about that? I don't know. Who gives a shit? All right. So the numeric value of a lowercase character is defined as its position, one indexed. Okay. So the numeric value of A is 1, and the value of B is 2, and C is whatever, and so on. Okay. So letters have values, I guess. Just making a little bit of some notes here. So we have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. And they have values associated. So this is value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm going to do them all. Let's just add spaces to each of these. I don't know what I'm doing, guys. Sometimes I surprise myself. All right. So 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. There you go. So each of these letters has a corresponding value. All right. What are we going to do with that information? The numeric value of a string consisting of lowercase characters is defined as the sum of its characters' numeric values. For example, the numeric value of the string ABE is equal to 1, 2, 5, and 8. Well, why is that? Well, we just look at this ledger, right? So A equals 1, and I forgot where the hell was the string that I was looking at. ABE. Okay, ABE, so before I forget. So B equals, from this, is 2, and E equals 5. So then when you sum them together, right, you sum those together, and you get 8. So that has the value 8. Makes sense, right? You are given two integers, n and k. Return the lexicographically smallest string with length equal to n and numeric value equal to k. Okay, so a lexicographically smaller. Okay, so we'll read this description and then I'll give you an example if this description, this formal definition doesn't make sense. But note that a string x is lexicographically smaller than a string y if it comes before y in a dictionary order, that is either x is a prefix of y or I is the first position such that xi comes before yi in alphabetic order. So basically, it's like alphabetic order in a dictionary, right? So, you know, this idea of lexicographic ordering, right, is the idea of what? Well, it's the following. The order of which things would show up in a dictionary. So sometimes it can be useful to think about a context of which some sort of ordering or whatever is actually used. That way you can think about it and be like, oh, okay, this is referencing this notion of how things are ordered in a dictionary. So how are things ordered in the ordered dictionary? Well, if you had if you had alpha and algebra, what would go first in the dictionary? Well, these two have the same letter, so they're the same there, then the same letter, and then once there's a different letter, whichever one comes earlier in the alphabet comes first, right? So A, B, C, D, E, F, G. So since G comes before P, it would be algebra and then alpha in a dictionary, right? So if they share some letters, you know, you just say, okay, they share this letter, so we can't use this to account for. right? You could literally just think of it as its numerical represent. No, you couldn't. But scratch that. But you know, you just think about it in order. You look at each letter, and then you look at the first letter where they're different, right? And whichever one comes sooner or earlier in the alphabet comes before the other one that you're comparing it to. Okay. So just to do another example, what if you had B? What if you had B and A? Well, we're just comparing these two to each other. So A comes before B, so it would be the order A, B. Silly, but I don't know why I did that, but maybe it's good to have another very simple example that's simpler than the first one I gave you. Okay. So you want to return the lexicographically smallest string of length n that has the numerical value equal to k. Right? So what that means is you want to find a string where when you calculate its value using this ledger here, the string would come as early as possible in a dictionary. Right? Because like when you have n equals 3, for example, so you have example n equals 3 and k equals 27. Well, for this, what we're trying to do is we're trying to figure out a string of length 3, so it has 3 characters, where its sum equals 27. Well, how could I sum to 27? Where I could make this a z, and a z has value 20. No, so I couldn't make this a z. I can make this I can make there's a bunch of ways of doing this. I can make this a j, because a j has value 10, and then I can make the next one an I guess. And an I has value 9, so it's 19, and I'm trying to get to 27. So to get to 27, I need an 8, and I can make this an H, right? So there's a countable amount, but there's a lot of combinations that you could do here, right? There's a lot of ways that you could combine 3 letters, n equals 3 letters, to get the total sum of 27, right? And this is 27 again because I'm using this ledger, right? This is 10, J is 10, I is 9, and H is 8. So 9 plus 8 is 17, plus 10 is 27 to get you 27. But we want something that meets the criteria such that it equals k equals 27, but it also has to be the minimum lexicographically placed string, meaning that it's the one that would come as early as possible in the dictionary. So that ends up being A, Y. And why is that? Well, A is 1, and Y is 25, right? If you look at this form here. So 25 plus 1 plus 1, 27. Make sense? Good. So how are we going to solve this? Well, I guess there's kind of two observations you need to make to solve this problem. The first one's a little bit more obvious than the other one. The first one is, well, you know, this is probably like there's probably some sort of greedy solution, right? Because we are trying to, find some minimum string, right? And I have to count up to k. So in order for it to have the least effect, I should do what? I should add the largest letters, meaning the letters that come the latest in the alphabet, at the end, right? And that's what happened here in this example, right? In this example, it can be seen that we did AAY, right? Well, because we want to make our string as small as possible, so we should put the largest things at the end and try to get the smallest things at the front, right? Because the smallest, you want the thing at the front to be the absolute smallest. That way, it comes as soon as possible in the dictionary, right? You want it to start at an A, right? Ideally, you know, you'd want everything to be an A, but you can't do that. So you'll stack the largest letters at the end and stack the smallest letters at the front, right? So I put the Y at the end because that's the largest letter, and then I put the smallest letters possible at the front. right? So there's a greedy solution here where it's like, I didn't do YAA, right? Because YAA, if you looked at a dictionary, YAA comes way after AAY. So you want to do a situation where, okay, I'm going to put the largest things to get the largest amount at the end because that'll have the least consequence on the placement in the dictionary. And then I'll put the smallest things at the front. That way that'll have the most effect on where I'm placed in the dictionary because the first character is going to determine where I'm put in the dictionary initially, right? If this is Y, if it starts with a Y, I have to go all the way to the Y section. But if it starts with an A, it's going to start in the A section, and then it's going to be placed within things that start with A, right? So it's like if you want your name to be called first, and it's in alphabetical order, and maybe it's in lexicographical order, right? You want to name your kid with something that starts with an A. If it ends in a Y or ends in a Z, that doesn't really matter, right? But if you want your child to be selected first in a list where they call people in alphabetical order, then you should put their name, you should make their name start with an A, right? You don't make it start with a Y or a Z, right? So we want this thing to be lexicographically small, so we want it to start with an A. But it also has to be some value. So if we have to stack up values, we should stack up those values at the end, right? And the second observation is then, well, we have to, like we have the idea of like how we want to stack things at the end, but how are we going to stack it at the end to ensure it's the smallest? Well, ideally, we'd have n A's, meaning we are given a constraint where we have to use n characters. And ideally, it would be okay, I'm repeating the same thing. Meaning we were given a constraint we have to use n characters of like sum k equal to k. Numeric value equal to k. So let's just start. So let's start at n1s and then update as far right as possible when we have to. So, for example, this example here is pretty good, right? Because what we're going to do is we're going to say, well, let's initiate that idea of these 2 points, right? Because ideally it would be all ones, but since it can't be all, ideally it'd be all A's so that I have the minimum lexicographical ordering, right? But it might not be possible for it to be all A's because it has to sum to K. So since we are constrained that we have to sum to K, well then we're going to have to add that in. So let's just add that in at the end because we have to. Let's not add it to the beginning because that's going to increase my lexicographical order, right? It's going to put me farther in the dictionary. So let's assume that it's all A's and then figure out what we have to tweak in order for it to meet this K value. And in order to have the least effect on this lexicographical ordering, let's do that at the end of the string as far to the end as possible, okay? So in this example, we have n equals 5, and we have k equals 73. Well, what we can do is we can say, well, how's this going to work? Let's assume that our string is 1, 2, A, right? That would be the ideal string of length 5, right? 1, 2, 3, 4, 5, and it's all A's, right? This looks pretty good. It's all A's. It's size 5, but the problem is it doesn't sum to 73. What does this sum to? Well, it sums to 1 plus 5 A's, which is 5 1s, so it sums to 5. So this is going to equal 5, but it's supposed to equal 73. So since it doesn't equal 73, we're going to have to increase some letters in order to get it to 73. Well, it's going to have the least effect increasing letters to 73 if we maximize starting from the right? Because you might say, well, if I'm trying to maximize something, I could do 2 things. I could do BY or I could do AZ. Which one is better lexicographically, right? These will have the same effect. Making this BY or making this AZ will have the same effect in terms of the K value, right? It's either 25 plus 2 or it's 26 plus 1. Well, this thing is going to come way before this thing in the alphabet, right? This thing comes way earlier. So if I want to maximize my score, I might as well maximize the end characters first, because if I don't maximize them when I can, meaning that maximizing this end character increases my score, right? Like you see that here, right? Like you maximize, maximize, maximize. You know, it's what? It's only going to make my score worse if I don't maximize it, if I'm going to have to use that character later, right? So I might as well maximize as much as I can in the current placement, because if I do it later, it's only going to make me later appear later in the dictionary. It's as best as I can say, but I think this point makes sense, right? Right, it makes sense to make it AZ instead of BY. Okay. So we have AA equals 5. So, and we need it to be equal to 73. So what can we do? Well, we can change the last character to a Z, right? Because that'd be better than changing it to anything else. Because even if I subtract out Z, well, that's giving me 26, which is 25 more. So that gives me 30, right? Because this was 5. Z is changing an A, minusing the A will make it 0 plus 26. So minusing 1 plus 25, right? To get me to 30. Now, this is still not 73. So my point is, well, it's better to use a Z here because I still have 30 left. So now I have AAA. Now what should I do? I should take another Z out. So now I'm adding another 25. So that gets me to 55. Now, AASZZ will get me to 73. Right? So the idea is just maximize the things you take out to maximize your score from the right, and keep doing that until you get K equal to 0. All right? So how are we going to do that in code? Well, what we can do is we can say, well, let's create this string that we're going to return, and we'll make it into a list. That way we don't have to update the list in linear time. Right? So we'll set everything to A initially. Right? So initially, the value of our list are all A's, like it is here. And then we'll update it accordingly to get it to 73 using this greedy approach where we change the last characters first and maximize them, because that'll have the least effect on the dictionary. Okay? So actually it's like this. And then the length of this thing is N. So that means that our K value, so we'll do it by minimizing the K value, right? We'll say the K value was 73 in the beginning. After we do this, it's 73 minus 5, which is what? 68. So 68. And then going downwards, downwards, downwards until it's 0 at the end. Okay, so we'll say, okay, now K equals K minus, well, now I have NA. So the value of A is 1, so minus N, right? And then we'll look at each element in the array, right? So we'll say for index in what? Well, we want to start at the end, right? We want to start at the end of the array because we want to maximize the end first and work our way back, right? We don't want to maximize the front because that's going to have the largest effect on our order. We want to maximize at the end first and work back because that'll have the least effect on our positioning lexicographically, right? So there's n elements, so minus 1, negative 1, negative 1. And then what do we do? Well, if K is greater than 25, right? Or no? Yeah. If it's greater than 25, then we might as well take a Z out, right? Because, like, when this value is 73, you know, if then it's 68 here, I might as well take a Z out because taking the letter out won't reach, I'm not to the end of the string. I'm gonna add a Z. I'm gonna replace this A with a Z, and I'm still gonna have so many left that I'm gonna have to go to the next one anyways. So if I know that I'm taking if K is still greater than 25, I have to change the current letter to a Z, right? Because that's what would be optimal. And then I'm gonna have to take K, and I'm gonna say K minus equal 25. Otherwise, we finally reached a character where this last character, right, like here, where it was an S, this last character can be the thing that we change. So 68 minus 25. Come on, Ben. 68 minus 20 is 48. Minus 5 is 43. 43 minus 25 is 43 minus 20 is 23. Minus 5 is 18. So then how do we get the S here? Well, there's 18 left. So since there's 18 left, it can fit within this range. So this is 18 plus 1, 19, because the difference of 18 from A to S to get it to be 0. So if it's greater than 25, then it's not going to fit in this range. So since it's not going to fit in this range, now I know this ends at 26, but it's 1 off, right? Because everything's already A, so it's a little confusing. But if it's greater than 25, then it's not going to fit in the range, so we're going to have to go to the next character in order to get to K equaling 0, right? As long as it's greater than 25, I'm going to have to keep just putting Z's inside that system to maximize my K value while making sure that my the lexicographic order of my string is as minimal as possible, okay? So otherwise we'd say, okay, well, L of I equals, what we'll do, so let's make the alphabet, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V. This works, I guess. We could also do like char or something. So we'll do this. Yeah, we'll do char order of A plus. So if the difference is 0, it stays in A. If the difference is 1, it becomes a B. If the difference is, right, because the difference here at this last one was, it becomes 19 becomes 18. So since it's 18, what's 18 characters away from A? Well, 1 character away is B, so 18 characters away is S. So plus 18, that would be for constant thing. And then at the end, you just return, turn this list back into a string in linear time once, instead of linearly changing the string every single iteration. And if this gets here, it's never going to get here, but maybe return -1 if it can't find the solution. Hey! Terrible solution today. As per usual, rambled like crazy. What is the runtime and the space? Okay. Okay, time and space. So for time, we have to look at all n characters at most, right? Because we have to look at all n. We could terminate early, but it's possible that we have to look at literally every single value in the end-length string in order to add up to this K value. So we look at all n characters, and then we do constant things, right? We do constant check, constant set, constant check, constant set. So we run n things, that's n time. And then for space, well, we have to create this return list of size n, right? Because we're returning that string of size n, so that's O of n time, space as well. All right, guys, peace out.